Today's lecture will be on seasonal and daily temperatures. The purpose of this chapter is that we want to see basically the interplay between the incoming solar radiation from the sun and the Earth's motions, which we'll learn about here in just a few moments. We'll look at these in terms of temperature variations on a seasonal basis. Basically, we're going to find out what causes seasons and also what causes daily and temperature variations. We'll start off with the Earth itself. It has two basic motions, and the Earth tilts, as you know. The Earth revolves around the sun approximately 365 days per year. You also know from your daily experience of the sun coming up, the sun setting, that it spins counterclockwise, the Earth, that is. If you look down on the North Pole, it does have a counterclockwise spin to it. And it rotates on its axis once every 24 hours. It tilts at about 23.5 degrees from the vertical and points toward a star. At this time I cannot recall which star that is. What we're going to look at today is we're going to look specifically at this tilt and see if it has any play in terms of our weather. Some basic information about the Earth's distance in orbit. The Earth is about 93 million miles away from the sun, and as you see from the figure there, has an elliptical orbit. The thing to note is, it's kind of interesting, we are a little bit closer to the sun in January than we are in July. You see right there 147 million kilometers during January, as you see right there, and 152 million kilometers distance in July from the sun there. So if we're closer to the sun in January than we are in July, it seems that we should be warmer, but we know from experience that isn't the reason. So really the distance from the sun doesn't play a huge difference. There's about a 7% difference in solar energy received, but not enough to make a difference in terms of temperature. So, what are the causes for our seasons? Well, one thing is the amount of solar energy received at the Earth's surface. We learned from the previous chapter, Chapter 2, that solar energy coming into the Earth is responsible for warming the Earth. We will also look at the length of time the sun shines each day. More energy available will tend to warm us up a bit more. Let's start off, first of all, by looking at these two diagrams. We're going to look at the amount of solar energy received at the Earth's surface. This particular graphic here is a picture of a flashlight. Notice when the flashlight is directly overhead, the intensity of the light is greater than as if we spread it out over a wider area. So again, it's the same beam of light, but the angle here is 0 degrees. This is coming in at about 30 degrees. The angle there is about 30 degrees approximately. And in this one, it's directly overhead. So we're getting the beam directly overhead. You see over here in the graphic to the right, if the sun is directly overhead, the intensity of the light is greater than as if it's spread out over a larger distance. Keep in mind, we'll also be talking about the atmosphere. The atmosphere, as we learned from Chapter 2, has some ability to attenuate the incoming solar radiation. Let's take a look at the length of time the sun shines each day. We see that more solar energy is received when the sun is available for longer periods. Your experience is that during the summertime, our daylight hours are much longer than they are, let's say, in January, February, and March. It has something to do with the tilt of the Earth, and we'll see that here in a few moments. But what you're looking at here in this particular area is just the different seasons of the year. The autumnal equinox, September 22nd, the winter solstice, December 21st, the vernal equinox, March 20th, the summer solstice on June 21st. You'll read about all of these in your chapter here in a few minutes. So let's take a look specifically at summer here. We have longer daylight hours. The sun is higher in the sky, but we want to know why. Notice I've made a comment here that the northern hemisphere is tipped toward the sun. So notice here that we are tipped, the axis is tipped toward the sun. So let's get a little bit closer in. And if you look at the Meteorology Now simulation, we'll begin to see this, and in fact, I will start it here in just a few moments. But notice the northern hemisphere. Notice that if we're looking down upon the northern hemisphere, the rotation is counterclockwise. So we're actually seeing this type of rotation about this particular axis here. If you notice, let's start off at a point of reference, the equator. If, as we go poleward, notice that the daylight hours begin to get longer. You can convince yourself by looking at the Meteorology Now simulation, and I'll play that, like I said, here in just a few minutes. But as we begin to go poleward, with this tipped, the daylight hours are longer. In fact, if we get up around the pole, you'll notice that they have 24 hours of sunshine. Let's run the simulation to see if we can see this. Okay, what you're looking at currently is an animation by Thomson Now, and you actually have access to this. What it is it shows the Earth in its different seasons. You see, as I'm pointing with the cursor here, as the sun, or as the Earth is revolving around the sun. Notice also that the Earth is tilted 23.5 degrees. And since we're talking about summer, let's go ahead and go on with a close-up here. Now, what I want you to notice, I'm outlining here the equator, and notice again the tilt of the Earth here, and notice the shadow indicating nighttime, and then of course the daylight. And notice as we go from the equator and we begin to move poleward here, the hours of daylight begin to increase. And in fact, by the time we get up to about north of 66.5 degrees north latitude, it's 24 hours of daylight on here. So again, you see that the day length begins to increase as the Earth during the summer solstice on June 21st is tipped toward the sun. And so therefore will maintain longer amounts of radiant energy coming in from the sun. And that's one of the things that we talked about for our summer, is that we're receiving more radiant energy, in other words, longer daylight hours. Now notice we just finished looking at the simulation, and a couple of things that you should have taken away from this is that the northern hemisphere is tilted toward the sun during the summer solstice. Something that you really could not have seen from the simulation is that the sun is directly overhead at about 23.5 degrees north latitude. That corresponds to the angle of tilt of the Earth. This is what we call the summer solstice. This is what you know as the first day of summer, June 21st in the northern hemisphere. What else did you notice about the number of daylight hours for the northern hemisphere at this time of the year? Again, as we pointed out, because of this tilt as we go from the equator northward, the longer sunlight hours along the latitude belts. And so we have an increase in the number of hours of incoming radiant energy. So the tilt plays a critical role. Well, what we know now, I have a question to pose to you. Since the polar latitudes, again, these polar latitudes up here has the longest periods of daylight, in fact north of 66.5 degrees, 24 hours worth of daylight. The North Pole, or at least the regions up in the polar area, is warmer than Iowa during the summer. True or false? Why or why not? Well, obviously this is false. We notice that the temperatures in Iowa typically are quite a bit warmer than the polar regions. Then why does this not occur? Did I just not say that the polar regions have the largest amount of sunlight, or at least the longest number of hours? Let's go ahead and look at figures 3.5 and 3.6 to see if we can answer this particular question. With figure 3.5 here, we see two lines. Well, first of all, let's take a look at the axes. Along the x-axis, we go from the equator all the way up to about 41, 42 degrees, which is where Iowa is located, all the way up to the North Pole, so that's our x-axis. So we're going from the equator, this region right here, on up to the North Pole. The y-axis is the insolation, or the amount of radiant energy, the short-wave radiation coming in from the sun. And so obviously as we go from bottom up to the top is what we're looking at in terms of insolation. We have two curves here. We have the amount of radiation reaching the top of the atmosphere, this one here in blue that I'm outlining, and then the amount of solar radiation that we receive at the Earth's surface, this bottom one. There's a lot of good information on this particular figure here, 3.5. Something that I do want to make clear, that I may not have made clear, is that insolation, the amount of radiant energy, is increasing as we go from bottom to top. So as we look at the amount of solar radiation received at the top of the atmosphere, notice here at the equator, going up to, looks like about 45 degrees, it begins to increase and then levels off, and then begins to increase again as we head toward the poles. And you can see that over here in the figure. You know, the sun's directly overhead at about 23.5, but you'll notice a couple of differences here. Notice here that the sun, or at least the radiant energy, is coming down directly, the shortest path through the atmosphere. And so more of the solar energy is concentrated in this area right here at 23.5. Here, notice, as I'm pointing right here, that it's going through more of the atmosphere and its energy is spread out. This goes back to the example that I used earlier of the flashlight. If you recall, let me just go back a few slides here. Again, if you'll notice right here, the flashlight shining directly down, producing an area of very bright light. We tipped at 30 degrees here, and notice that the same amount of light is spread out over a longer region. Okay, so what we're seeing is that we're seeing, yes, more direct sunlight here, less sunlight here, or at least less radiant energy. Some of that is being attenuated by the thicker portion of the atmosphere as it's spreading through that portion of the atmosphere instead of directly overhead. So the angle of incidence does play a role in this particular area. Well, let's continue on with this discussion. The sun angle is lower, but there are 24 hours. So we're beginning to see that this maximum here, again, this top curve here is the amount of solar radiation reaching the top of the atmosphere. Notice that, yes, we are spreading the amount of energy out here in figure 3.6, but again, during the summer solstice, notice that there's 24 hours of sunlight. So the top of the atmosphere is still receiving quite a bit more energy. But again, that doesn't answer the question, why is Iowa warmer during the summer than, let's say, the North Pole? Well, it has something to do with this lower curve here in figure 3.5. Now, this is the amount of radiation, or the amount of solar energy that is actually reaching the Earth's surface. Recall from our discussions in Chapter 2 that ozone up in the stratosphere absorbed some of that radiation coming in from the sun, and then the rest of the atmosphere, especially in the visible region, passes all of that radiation down to the surface of the Earth. And so you'll notice, as we go from the equator on up to about 30 degrees north latitude, we have a maximum. And then as we go toward the poles, the amount received at the Earth begins to decrease. Now, why the maximum here at 30 degrees north latitude? Why not here at 23.5? We see that the sun is shining directly overhead at the summer solstice at 23.5 degrees, yet the maximum amount of radiation that's received at the Earth's surface is at about 30 degrees north latitude. That's yet another mystery that we'll solve here in a few minutes. But now, Iowa, where we're at about 40, 41 degrees north latitude, so we're somewhere in this area right here. notice that, again, the top of the atmosphere, we receive less energy than over here at the North Pole. And part of that has to do with the fact that the poles receive sunlight 24 hours a day. And so they're beginning to accumulate more energy than we are. But if you'll notice down here, let me go ahead and erase some of this. This is getting to be a bit messy. Now, again, if you recall here, notice the amount of energy, or the amount of incoming solar radiation that we receive. And Iowa's about right here. Okay. Compared to the North Pole, is quite a bit less. So we're receiving more, at least more incoming solar radiation at the surface than the North Pole does. So that's one of the reasons why Iowa is quite a bit warmer than, let's say, Alaska or even further north. So what physical mechanisms are responsible for the differences between these two curves? Well, I hinted in the last slide. Part of this has to do with as the Earth is, or as the radiant energy is coming into the atmosphere, as you recall from Chapter 2, some of that energy is scattered back by clouds. Some of it is absorbed. Like I said, ozone absorbs some of that incoming radiant energy very high up. And then some of it's reflected by the particles that we have in the atmosphere, dust, volcanic ash. Things like that will help reflect some of that incoming solar radiation. Reason number 2, the thickness of the atmosphere penetrated. So if we look over here at figure 3.6, you'll notice that the thickness, if you think about the shortest distance between 2 points, is a straight line. Well, we see here the distance penetrated is a lot shorter here through the atmosphere than through this particular path right here. Also, the presence of cloud cover, snow, and water. In other words, albedo, which I'll define here briefly, and we'll get into albedo in a little while. But albedo is the amount of reflectivity of an object. Snow has a high reflectivity. You notice that when you're walking out in a snow-covered field. The sunlight coming up off the snow creates snow blindness, so it has a high reflectivity. Water also has a high reflectivity, especially still water. Cloud cover also has a high reflectivity. And then another physical mechanism is at 30 degrees north latitude, which is where we see the maximum amount of energy received at the surface, is an area where most of the world's deserts are located. Now, we'll learn a little bit later why the desert regions are located at 30 degrees north latitude. It has to do with general circulation patterns, which we'll get to in a little while during the semester. But there's an absence of cloud cover, an absence of moisture, and again, if you recall from Chapter 2, energy partitioning, incoming energy. If you have very little moisture, there's the energy coming in being used as what we call sensible heating. All that heat energy is being used to actually heat the Earth's surface. If you have moisture present, some of that heat energy coming in is being used for evaporation, which we call latent heat. When we begin to evaporate, condensation is also a process that involves latent heat release. But these are the mechanisms that are responsible for what we described here as a warmer climate here in Iowa compared to further north at the poles. One more question. We know that the sun is overhead at 23.5 degrees north latitude. Then why the maximum solar radiation received at Earth's surface, why does that occur at 30 degrees north latitude? Well, we just answered that. That has to do with the desert regions, absence of moisture, lack of cloud cover, little vegetation in that particular area. At about 23.5 degrees north latitude, you have quite a bit of cloud cover. You have quite a bit of vegetation at the Earth's surface at that particular point, and so all the energy coming in is being partitioned between evaporation, condensation, and less of it's left for sensible heating. What I'd like you to do at this point is just to take some time to read pages 59 and 60, which focus on the rest of the seasons, such as the autumnal equinox, the winter solstice, and the vernal equinox. I wanted to pick one season, summer solstice, just to cover in detail some of the same principles that we've used here will apply to the other seasons. Okay, I think it's time for a brain teaser here. Since we know that each day after June 21st the days shorten, okay, our longest day typically occurs on June 21st, then why are our maximum temperatures reached in August? Shouldn't our hottest day of the year be June 21st? Rarely does that happen. We see plenty of July, August, and even some September days where we have our highest temperatures. What I'm going to ask you to do is I'm going to ask you to experiment with one of our simulations. It's called Budget Sim, and I want you to use the simulation to answer the question above. This is really a critical concept for you to grasp. And so what I'll do at this point is we will go ahead and pause the video just for a few minutes so you can go to this particular link and Before we begin Budget Sim, I would like to explain a little bit about how to use Budget Sim. What you're looking at here, of course, is a tank filled with water. Currently it has about 20 liters worth of water in the tank. You'll notice that you have an output valve here and an input faucet up here at the top that I'm marking with the cursor. If we look to the right, we have a couple of graphs. We have the level on the y-axis here, and then the time going from 0 to 24 hours on the x-axis in the top graph. The bottom graph is also one of time in the x-axis, and then the rate of inflow here. So the difference between these two graphs, the top one has the level of water in the tank in the y-axis, and here is the rate of input into the system. If we go over here to the left, we see that we have a way to control input. And if I were to start it, initially when I start this, the water will drain out of the tank for 6 hours. So from 0 to 6 hours it will drain at about, or actually at 1 liter per hour, as stated here under the cursor. So let me go ahead and just start this. Notice water level is now dropping to 14. We're on hour 6. Let's take a look at the graph. The level has dropped from 20 down to 14. We see we're on hour 6. Notice that the graph here, the rate of outflow is constant. It's 1 liter per hour. So every hour, 1 liter is going out of the output faucet here, and you control how much goes in with the faucet, the input faucet. So let me just go ahead and I'll slide the bar here. Again, this is the input bar. Notice initially I can go 2 liters per hour, and we'll go ahead and run this. So for hour 7, we went from hour 6 to 7. We now notice that the level is going up slightly. And we can see this right here. The level is going up slightly here. Now we're up to 15 according to the water level here. If we look at the rate of input into the system, again, notice that the output, the water going out of the tank, is constant, and now we have actually increased it here to 2 liters per hour. Now I can go ahead and control this again, and I can move it up to 3 liters per hour or up to 4. I'll just go ahead and do 4 here. We'll do it for 1 more hour. And you'll now notice that the water level is up to 18. And again, you'll notice that level rising up here. In hour 8, we're up to now 18. And again, the rate of input into the system is listed here. If we go over here, listed as 4. So again, we can increase this. We can increase this to 8, or actually 6 liters per hour, or 5 liters per hour, or 4, or 3, or we can even bring it down to 2 liters per hour. Let's see, if I were to do that, I've got 2 liters going into the tank, 1 coming out, so I should, over the next hour, have a net increase of up to 19 liters in the tank. So we'll go ahead and do that. And you see that now 19. Now notice that the rate of inflow, again, I've brought it down to 2 here in the bottom graph. And now we're up to 19, so we've actually increased. So you see how to do this, and you can control this slider bar, the input, how much you're putting into the tank, up through hour 18. And then after that, after hour 18, the tank will drain for the final 6 hours at 1 liter per hour. The object of this particular simulation is we want the level, the maximum level, shown by this graph up here, sometime during this 24-hour period to be 70 plus or minus 2. Okay, so we're looking at 70, so it can be anywhere from 68 to 72 is what we want this particular tank to be. And you can adjust that by going through here. Now obviously I'm having you do this simulation because it replicates physical processes in the atmosphere. Now think about this. We've been talking about radiation to date. During the current module, we're talking about temperatures and how temperatures are affected by radiation. Keep in mind, radiation coming in from the sun warms our surface. The Earth's surface, or any object on the Earth's surface, is constantly radiating long-wave radiation, infrared radiation. And so obviously this particular simulation has something to do with those physical processes. What I'm going to ask you to do, once you've successfully completed this simulation, again, a successful trial is that the maximum level is anywhere from 68 to 72, somewhere in that 24-hour period. I'm going to ask you to look at these graphs and see if you can, by your interpretation of the graphs, I'll ask you a few questions and see if you can determine what physical process is being replicated here. So good luck with this, and we'll pick up with this a little bit later in the lecture module here. Well, have you figured out the brain teaser by using Budget Sim? We'll come back to that just in a few minutes, but I hope that by using Budget Sim you can answer the question here, why our maximum temperatures typically are later in the summer after we receive maximum insolation from the sun, which would occur on June 21st. Let's just briefly look at the southern hemisphere. We've been focusing most of our time up where we live at, but let's look at the southern hemisphere. Now notice, in December, the southern hemisphere is pointed toward the sun. Notice that we have the tilt. Again here, if we look from the vertical, the angle here is 23 degrees. There is a tilt. And so that in December now, the southern hemisphere has longer daylight hours. And we know that longer daylight hours mean that we have more incoming solar radiation. So this typically in December would be their warm season down in the southern hemisphere. So in the above figure, I have a little quiz here for you. The southern hemisphere is tilted toward the sun in December, so this would be their, that's right, their summer solstice. Again, it's the tilt of the Earth that causes the seasons. We'll also take a look at the sun's path and position across the sky. Now we've got a couple of figures up here. The one on the left here is down at 23.5 degrees south. Now again, we're looking at the southern hemisphere here. So that in June, notice the path, the sun rises in the northeast and sets in the northwest. The sun path in June is shorter than the sun path in December, which, by the way, corresponds to their summer solstice. Okay, so longer path of the sun. Also notice that it's higher up in the sky compared to a low sun angle here in June. And we recall that when we have a low sun angle, the energy is spread out, as in the example that we used earlier in this module with the flashlight. And also notice that the atmosphere penetrated by the sun's rays is actually scattered, reflected, absorbed when the energy is spread out, whereas when it's at a higher sun angle, more of it reaches the Earth's surface. One thing that I think is kind of interesting here, note that in this particular picture here, that in the southern hemisphere in January, the distance actually from the Earth to the Sun is 147 million kilometers, and if in July it's 152 million kilometers. So the southern hemisphere, the southern hemisphere is tilted toward the Sun, and the Earth is closer to the Sun at this time. So you would think that the summers in the southern hemisphere would be warmer than the summers in the northern hemisphere, because we're further away in the northern hemisphere from the Sun when the northern hemisphere is tilted toward the Sun. However, this is not true. In fact, the northern hemisphere summer is warmer on average. So we need to ask ourselves why. Now, you've been given enough information over the last couple of lectures to kind of figure this out. It probably has something to do with energy partitioning. So let's look at it, this particular slide here. You'll see that I have a picture of the Earth, three aspects of it. Here you see the North American continent here, South America, the equator is somewhere in this area here. And again, we see the continent of Asia over here. Again, the equator is somewhere in this area. And then we have the continent of Africa. And again, it's somewhere in this area here is the equator. Now, what do you notice? The difference between the northern and southern hemisphere. Well, the land mass. We have more land in the northern hemisphere typically, well, we do, not typically, but always, than you see in the southern hemisphere. And so we have more water coverage, more oceanic coverage. And if you recall from the partitioning out of energy, the sun's radiant energy coming in, some of that energy is being used to evaporate the water. And so less of it is left for sensible heating to raise the temperature. Whereas in the northern hemisphere we have more land mass, and some more of the incoming radiant energy is used to raise the temperature instead of evaporation. Keep in mind that water has a larger heat capacity. Also, the second factor in this, because of the elliptical orbit, and this is interesting, you'll notice that as we head from September to March, again, keep in mind that in the southern hemisphere, this is the warmer days, the summer. There's 179 days when we go from September to March, whereas when we go from March 20th to September 22nd, which is typically when we move from our vernal equinox into our summer solstice, you'll notice it's 186 days. So we have a week more of being tilted toward the sun than the southern hemisphere has. So the combination of more land in the northern hemisphere and a week more path where we're tilted more toward the sun accounts for, in part, the warmer northern hemisphere summer. Let's go ahead and focus now more on local seasonal variations. One of the first figures I'll bring up is a figure from your textbook, figure 3.8c. It's for the middle latitudes, 40 degrees. This is where we're located at in Iowa, right around 42 degrees north latitude. This particular picture obviously shows directions, northeast, south, and west, and then the different paths across the sky. For instance, the sun path during June, notice that it is at its highest point above us in June. And as we go through the equinox, the path length begins to decrease, and then by the time we hit the winter solstice, the sun is at its lowest position in the sky, and its path length, the number of hours of sunshine, is small compared to what we receive in June. But also notice that in this particular graphic, that the sun is oriented in the southern portion of our sky as it's going up. It's at its highest point, like I said, over June, but again, the tilt of the Earth playing a role in this. So basically what ends up happening, southward facing objects will receive more direct sunlight than northward facing objects. And we'll talk about the implications there in the next few slides. Typically, southward facing objects are warmer, thus we have more evaporation. Soil conditions are typically drier on the southward facing objects or slopes or hillsides, which means that more of the energy goes into sensible heating. In northern latitudes, hillsides usually have a longer growing season. In mountains, snow lasts longer on the northern slopes. Therefore, most ski slopes or ski runs are built facing north. For your homes, you'll notice a lot of homes, especially in northern latitudes, usually have south-facing windows. This is to take advantage of the sun. Recall, even during the wintertime, the sun comes up in the southeast, reaches its highest point, sets in the southwest, so southward-facing windows are an advantage. Now, during the summer, again, you see right here, during the June position of the sun, you would need to have some eaves to help block out some of the incoming solar radiation to shade those same south-facing windows. Well, let's get even smaller in terms of a time scale. Let's talk about daily temperature variations. Part of this course, as you know, is weather forecasting, so you need to understand how temperatures change. You've experienced this, a typical cycle during the day. Typically, we begin to get warmer during daylight hours, and we know because of the incoming solar radiation, this is part of the reason. And at night, we begin to cool off as the source of the incoming solar radiation, the sun, is no longer a factor in the evening hours. So again, the Earth receives the most intense solar rays at noon. However, the maximum temperature occurs later in the afternoon. Now, why is this? Seems strange, doesn't it? Well, let's revisit Budget Sim for a few moments, and I think this will make it clearer. Now, what I've done here is I've actually completed Budget Sim. My maximum water level, it looks like, was right at about 70. There are quite a few things that I'll point out on this particular slide. But let me go ahead and just... The top graph here, again, is the water level. And you see here that the water level begins to increase as I go through hours 7 through, it looks like, about 18, and then begins to decrease. Notice the bottom graph here, this solid blue line that I'm outlining. This was the rate of outflow, 1 liter per hour. That's constant throughout the entire 24 hours. And then the flow rate, what I put into the system. So notice I started off here at hour 6. You see 4, 6, 8, and then I reached a maximum of 10 liters per hour input. And then I begin to decrease what I put in the tank. As I head toward 18, I begin to increase it slightly here. But notice as I get down to hour 18, my rate of input begins to decrease. Now you notice I have a couple of green lines here. Let's ignore those just for the moment. But what I want you to notice by looking at this particular graph is that this incoming water faucet is analogous to the incoming solar radiation that we have in the atmosphere coming in from the sun. So the energy that I'm inputting into the system, namely the water that's going into the tank, is analogous to shortwave radiation coming in. And so as we begin to look at this rate of outflow, this 1 liter per hour, is analogous to the long-wave radiation. Recall that any object on the Earth emits long-wave radiation, typically in the infrared region. And so if we look at the budget in terms of short-wave radiation and long-wave, again, this is the long wave. And then this particular graph here, at this point of the graph, is shortwave radiation. Notice that I have more incoming shortwave radiation, or actually I have more water going into the tank than going out of the tank, as long as I maintain my rate of input larger than the rate of output, which is 1 liter per hour. And so, also notice this top graph, the water level begins to increase. And you notice it increases as long as what? As long as what we input into the system is greater than what we output. So as long as I'm continuing to put more water in here than coming out, the tank level begins to rise. Now notice right here, I've got a couple of green lines. And these particular green lines, this particular point here is the beginning where the amount of water I put in is greater than what's coming out of the tank. And so once that begins to happen, you begin to see the water level rise. And now we begin to see a decrease in the water level, and that decrease begins to happen as I reach this point where my output, what's leaving the tank, is greater than what I'm inputting. Do you recall the brain teaser I had just a few moments ago, where we talked about the incoming solar radiation being a maximum back in June, but our warmest temperatures typically occurred in August and September? And I asked you why. Well, we can actually gather the information by looking at Budget Sim again. Recall that in this particular simulation, that the maximum rate of input, the maximum amount that I was putting into the tank, was at 10 liters per hour. And that maximum occurred, it looks like, somewhere right around between hour 10 and 12. Somewhere in that area. This was the maximum output. However, the maximum level wasn't reached until over here in hour 17. Now, why is that? That looks very much like what we talk about with the maximum amount of solar radiation coming in June, but yet the maximum temperatures occur in August and September. Now, the reason for that, recall, is that again, as long as we're still putting in more than what we're taking out of the system, the water level continues to increase. It's just like that in the natural system. As long as we have more energy in terms of shortwave radiation coming in than leaving longwave radiation than what the Earth is emitting, we will continue to heat up the system. So this is analogous to being June all the way out to September. We're still adding in more shortwave radiation than what's leaving, and so our temperatures will continue to rise. Thus, we have the maximums that occur later in the summer. You should probably spend a few minutes at this point to go to the Thomson Now site and work with the energy budget simulation that they have. Just to remind you, if you haven't used this particular simulation, you can choose by location. This particular location is in Mississippi, the time of year, in other words, season, and then you can play a 24-hour period down here to see the effects of the Earth, atmosphere, and incoming solar radiation budget. And I would encourage you to spend a few minutes looking at that. Well, let's talk about daily temperature variations, specifically daytime warming. This particular graphic here, there's a lot of information going on here, but we have an x-axis, which is temperature in degrees Celsius or Fahrenheit, and then the altitude as we go from the Earth's surface on up. And as a point of reference here on the right-hand side, they show a meteorological weather instrumentation shelter. It's about 1.5 meters or about 5.5 feet above the surface is where the temperature is taken in a ventilated type enclosure. But what we want to look at here specifically is how temperature changes with height during the day with very little wind. Notice that, again, this is surface. We could list this as 0 meters up to about 1.5 meters here. And we see that temperature very near the surface, in this particular example, if we look at it in terms of degrees Celsius, is about 55 degrees Celsius. As we go up in altitude, what do you notice? Well, you notice temperature decreasing. Okay? And we would expect that with the incoming solar radiation heating the Earth's surface. And recall that the atmosphere is pretty much impervious to the incoming shortwave radiation, except for ozone. Ozone will absorb some of that incoming shortwave radiation. But on a cloudless day with very little winds, that's basically what we're looking at as far as a temperature profile. We see as we go up in altitude, temperature beginning to decrease. The temperature at this particular altitude is about 36 degrees Celsius. And as we go even further up, those temperature continues to flatten out a little bit. But our warmest temperatures will be near the surface, again, which is what we would expect with incoming solar radiation. And then temperature decreases rapidly as we head up into the atmosphere. Now, with windy conditions, however, the temperature profile will change a bit. Again, notice this particular line, temperature decreasing with height. This is the condition on a calm afternoon. But in a windy afternoon, we begin to have convection taking place. Recall we talked about 3 methods of heat transfer in the atmosphere, one of those being convection, where we begin to get air rising because it's hotter, and then you begin to mix some of the air, take some of the cooler air here, mix down to the surface, take some of the warmer air at the surface and begin to mix it upward. What this ends up doing is flattening out the temperature profile here. Temperature is still decreasing with height, but not as rapidly. Let me clean this up a little bit here. Again, with windy conditions, we redistribute the temperature profile by mechanical convection. In other words, the wind is providing aid to transfer energy throughout the atmosphere. So instead of the temperature being up near 50 degrees Celsius on a windy day, we might see something around 40 degrees Celsius in this particular example. And then as we go up, temperature decreasing with height. If we go up to 2 meters, we see the temperature is at about 100 degrees Fahrenheit at about 2 meters, whereas down at the surface, the temperature is about 103 degrees Fahrenheit. So, this is one way that we can use energy transfer throughout the atmosphere is through convection. Again, we talked about that back in Chapter 2. So a windy day actually helps to mix the atmosphere. In other words, to flatten out the temperature profile, as I mentioned before. Now, this particular graphic should look somewhat familiar. This particular part of the graph is temperature versus time of day. This is sunrise right here, sunset right here, and then basically what we have are 2 graphs in one. This particular bottom graph here that I'm outlining is the amount of energy coming in versus time down here on the x-axis. I'll clean this out so you can actually see it again. Let's take a look at, first of all, at the bottom graph here. Now, notice that we start here at midnight, and we go all the way through sunrise to noon to sunset, and then back to midnight. Now, the blue curve here is the long-wave radiation. This is the energy leaving the Earth. Recall that anything that has a temperature emits radiation at different wavelengths. So we have the amount of energy as we head toward sunrise. The Earth has been emitting energy all evening, and so as we begin to hit sunrise, we see this curve here beginning to take off. This curve here is the solar radiation coming in from the sun, and so our shortwave radiation increases to a maximum right around noon, and we're still receiving solar radiation from the sun all the way to about, in this example, to about 4 o'clock. is where we have this positive energy. In other words, the energy coming in, being the sunlight, versus energy leaving the Earth, which is the long-wave radiation, we have a positive addition of energy into the system, which means we should see temperature increasing, which is what we do in this top graph. As long as the amount of short-wave radiation coming in exceeds long-wave radiation leaving, then we should see an increase in temperature. And this is what we see. And in fact, we see the maximum temperature occurring at about 4 o'clock. And this corresponds, let me clean this up here again just a bit. This maximum temperature here corresponds to the point where incoming radiation is equal to outgoing radiation. At this point, we're still receiving incoming solar radiation from the sun, but it's decreasing as we head towards sunset. And now you notice that we have more energy leaving the Earth, shortwave radiation indicated by the blue line, than we have coming into the system, which is shortwave. Long wave leaving the Earth, shortwave energy coming in. So now we have a deficit of energy, and we begin to see temperatures cooling. This is just what you saw in Budget Sim. Now you'll notice in the example I have here, we could look at this in terms of a bank account. The blue line here being money taken out of the bank, the brown line here being money put in the bank, and as long as we're putting more money in the bank than we're taking out, then we have positive cash flow here. However, if you get into a situation where you're taking out more out of your bank account than you're putting in, then you have a deficit, or you begin to bounce checks. Then you run into problems. So it's any type of budget. In this particular case, we're looking at the energy budget into the atmosphere. So that's the reason why maximum temperature typically occurs later in the day, because we're still receiving more incoming shortwave radiation than we're losing. Now, we're assuming that there are no significant cloud cover or passage of fronts. We also assume that there's not a large body of water nearby. In other words, in terms of a maximum temperature occurring later in the afternoon. As we're going to learn this semester, cold fronts, warm fronts, as we've already learned, cloud cover plays a role in keeping temperatures down during the day and keeping them up at night. And we also know that large bodies of water have a very high heat capacity. In other words, it takes a tremendous amount of energy input into an ocean or a body of water to raise the temperature by 1 degree Celsius. So you can think of large bodies of water as huge heat reservoirs. And so that impacts. You remember we were talking about partitioning of energy. Do we use that energy coming in from the sun for sensible heating, which would raise the temperature, or do we use it for evaporation, which would be latent heat? And that's what I've mentioned here, just the idea of energy partitioning. Also keep in mind the types of soil moisture content, and vegetation. Any of these can remove or can help to partition it off in terms of sensible and latent heat energy. Now, one thing I'd like to point out down here, notice that the region around 30 degrees north and south latitudes are examples of where most of the heat energy is being converted into sensible heating. We talked about this being areas where there are deserts, very little cloud cover, little or no moisture, little or no vegetation. So that's one of the reasons why we were talking about, although the sun is directly overhead at 23.5 degrees north and south latitude, depending upon the season that you're in, at 30 degrees north, there's really not a whole lot of partitioning of the energy. In other words, most of the energy is being used to heat the Earth's surface. And so that's the reason why we have 30 degrees north being some of the warmest areas. Let's take a look at nighttime cooling. Quite a bit different than what we see with daytime cooling. In fact, again, this particular graph here is altitude as we go from 0 meters up to, this is about 1.5 meters. Again, I'm using this weather shelter as a point of reference, sitting at the surface, and goes up to about 1.5 meters. You'll notice that temperature in this particular example is about negative 0.5 degrees Celsius at the surface. If we go up to about 1.5 meters, however, we see the temperature warming to 4 degrees Celsius. So now we have temperature increasing with height. Do you recall why this is happening? If you recall from radiation sim, we'll talk about that here in a moment, the atmosphere is a poor absorber and emitter of radiation in most cases. The ground itself is a very good emitter, depending upon soil content, depending upon moisture, vegetation, things like that. We'll come back and take a peek at that in a moment. But notice, temperature is increasing with height in the evening hours. And this is with very little wind. In other words, we don't have any type of mixing. So what are the physical mechanisms responsible for the nighttime cooling? Again, keep in mind this particular slide here where temperature is increasing with height. Let's talk about some of the physical mechanisms responsible. Well, we know that when we have more energy leaving the system, in other words, when we have infrared or long-wave radiation leaving the Earth, more leaving than incoming, we will see temperatures cooling. Also keep in mind that infrared radiation is being constantly absorbed and emitted by the Earth's surface 24 hours per day. In most cases, we typically lose more infrared energy than we gain, thus we cool. Now, at this point, we can define this type of profile where temperature is increasing with height. We call this radiational cooling. When the ground and the air directly above the ground are cooling because of the emission of long-wave radiation. In other words, it's losing energy. The average speed of the molecules begin to decrease, and recall that's how we define temperature, as the average speed of the molecules. So my question to you, which is the better radiator of infrared radiation? Is it the ground or the atmosphere? Let's take a look at the graphs below. Now this particular graph here is from RadSim, and this is over a freshly packed snow surface at night. And notice, right at the surface, again this y-axis being altitude in meters and temperature in Fahrenheit on the x-axis. Notice that temperature is increasing rapidly as we go from the surface and then begins to decrease once we reach this point up here. So what do you recall? Well, from this particular example, you would say that the ground is a much better emitter of infrared radiation. And we see this because the ground right near the surface is the coldest part. In other words, it's emitting most of its radiation. And the air directly above it, there's some transfer of energy there by conduction, but very little, since the atmosphere is a poor conductor in terms of thermal conduction. So, right after sunset, you see the Earth's surface is slightly cooler than the air directly above it. However, there is some transfer of energy, like I mentioned, by conduction. So we take some of the warmer air directly above the surface and we transfer it down to the surface, but the surface quickly radiates it away as infrared energy, and so it stays colder. At night, the ground and the air in contact cools more rapidly, like I said, because it continues to lose energy much more quickly than the atmosphere. We do have some transfer, like I said, from the warmer atmosphere to the ground, but this is a very slow process because of the problem with the air's thermal conductivity. We talked about that in Chapter 2. So now you have a pretty good idea of why temperature begins to increase with height at night. Now, just like during the daytime, we can have some forced convection, the winds. This particular temperature profile occurs during a windy evening. Notice we still have temperature increasing with height, but it's more of a gradual slope compared to this particular change in temperature with height on a calm night. So again, we take some of the, if we have windy conditions, we take some of the warmer air. If we were to look at this temperature profile here, we take some of the warmer air, transfer to the surface, some of the cooler air is brought up, and now your temperature profile begins to flatten out a bit. So a little bit warmer here compared to in the calm winds, but now a little bit cooler up here compared to what you would see on a calm night. Now, I've been talking about temperature increasing with height. there's an actual term for this. It's called a temperature inversion. And in fact, when that temperature inversion is caused by infrared radiation being emitted from the ground in terms of long wave energy, we term this radiation inversion. Okay, so temperature is increasing with height because the surface is losing its energy in terms of long wave radiation, and so it begins to cool. So what are some atmospheric conditions needed for radiation inversions? Well, we've already identified this: windless nights, or very light winds, because we don't want to promote mixing. In other words, warmer air from above being brought down to the surface and some of the cooler air from the surface brought above. If you want a strong radiation inversion, which is what this temperature profile looks like, strong increase of temperature with height. Notice the temperature changes here at about 29 degrees Fahrenheit at the surface, up to about 10 feet in the air. It goes to almost 38. There's almost a 10-degree change over 10 feet in a very calm night. Well, you need long nights. We talk about radiation inversions occurring because the Earth is losing infrared radiation. The longer the night, the more infrared radiation the Earth can continue to lose, assuming that we have clear skies. Now, keep in mind, back in Chapter 2, we talked about clouds absorbing that radiation coming from the Earth and emitting their own infrared radiation back to the Earth, thus keeping temperatures up. So if you want a strong radiation inversion, in other words, a strong increase in temperatures with height at night based upon the Earth losing radiation, you need clear skies, dry air, snow covering the ground. Snow is an excellent emitter of infrared radiation, and so snow covering the ground. Loose soil. You want to keep the heat that's in the ground, you want to keep it away from the surface, and the best way to do that is have loosely packed soil. You have air pockets in between the different soil particles. And we know that air is a poor thermal conductor. And so if you have that air space in the soil, it's not going to promote heat transfer from subsurface to the surface. And then, of course, a lack of vegetation, because vegetation can actually produce some problems with radiation inversions. At this time, what I'd like you to do is just take a few minutes to read a couple of pages there on thermal belts and protecting crops from the cold. I won't go into any detail here, but you will be responsible for exam questions from this particular area too. So just spend a few minutes, if you would, reading through that. Well, let's talk about controls of temperature. We've actually talked about some of these factors. We'll identify the main factors that cause variability in temperature. After all, you're going to be forecasting for temperature, and so we need to find out why temperature is different from place to place. Now, we've already talked about a temperature difference between the North Pole and Iowa. We talked about incoming radiation, at least at the top of the atmosphere, being greater over the North Pole than it is over Iowa at certain times of the year. But yet we're warmer, and we talked about the reasons behind that. We already identified the greatest factor in determining temperature. That's the shortwave radiation coming in from the sun. But we'll also talk about other factors that influence temperature variability. First of all, the latitude that you're located at, the land and water distribution, ocean currents. Now, we haven't really talked so much about ocean currents yet. We will get into that in later chapters. But you may have heard of the Gulf Stream, which is a current of water that runs along the east coast of the U.S., typically warmer waters, which tend to influence land temperatures along the east coast of the U.S. Elevation, we'll also talk a little bit about that. Now, what you're looking at here is a map, longitude along the x-axis, latitude. You see the North American continent here. We'll look at that particular area as we look at this particular map. There's a lot of information here. And you're looking at temperatures. Now, these lines of temperatures, in other words, 70-degree temperature line runs all the way through here. And I'm going to give you a definition here. It's called isotherms. And an isotherm is a line of temperature. It's a contour of temperature. Everywhere on this 70-degree line indicates that temperature is 70 degrees. And you'll notice that as we go poleward, now this is average January temperatures. As we go poleward, temperatures begin to change, and they change rather rapidly. If you look down here along the Louisiana Gulf Coast area, we see temperatures, average temperatures in the 50s. We go up into Iowa, just a distance of about 1,000 miles. The average temperature jumps down to about 25. So we have a change of 25 degrees Fahrenheit over 1,000 miles. So temperatures change rapidly. There's also quite a few things here to notice. Notice that the temperature lines, the isotherms, are packed together much more closely over land than they are over the ocean. Temperatures do change over the ocean, but they change much more slowly. You have to go a larger distance. For instance, if we take a look at a latitude line here along the Gulf Coast, and we see an average temperature of 50. Well, if we go directly over to the coast, we see temperature here starts at 60. And to go to 0, you have to cover a larger distance going from 60 to 0 compared to doing the same thing over land. Let me see if I can clean this up just a bit. Again, going from, well, let's say we'll go 60 here to the 0 line, and going 60 to the 0 over here. Notice this line is quite a bit longer than this line here. So temperatures change much more rapidly over the continent in January than they do over oceans. Any idea why? Well, you already have an idea. We talked about the ocean being a huge heat reservoir. In other words, it has to do with heat capacity, or specific heat in particular. And so the land cools and heats up much more quickly than the oceans. Also notice that the isotherms, that's the lines of constant temperature or equal temperatures, over the continent begin to point downward. Whereas over the ocean here, over the Pacific Ocean, they begin to point upward. Down over the ocean on this side, they begin to point downward. And notice right along the coast is a change where lines or the isotherms begin to spread out. Here they're tightly packed together, still tightly packed together, but as we go into the ocean, they begin to spread out. Same thing here, tightly packed together, here they begin to spread out. So anywhere you have an ocean continent, and we can look over here, the same thing. Look over here. We have the temperature lines really bending out here, bending upward. So what's the cause for that? One other thing I'd like to point out as we're looking at this, notice that the isotherms, the lines of equal temperature, begin to oscillate up and down. But here, over the southern hemisphere, you can pretty much draw a straight line. What's the reason for that? We have a little bit of bend there, but we have a lot of bending in the northern hemisphere of the isotherms compared to the southern hemisphere. We've already hinted at that. That has something to do with the distribution of land and ocean. There's much more water in the southern hemisphere than there is in the northern hemisphere. We talked about heat capacity, and so there's not a large change in temperatures with large bodies of ocean. Well, let's take a look at the average July temperature. Now, notice over the North American continent here. Obviously, temperatures are warmer. And, however, there aren't as many isotherms present. Okay, let's back up here a second. I'll clean this up here. Notice quite a few isotherms here. In other words, temperature changing rapidly as we go from north to south. However, here we looks like temperatures here in the south are in the mid 80s. We go up into Iowa and we see average temperatures here in the mid 70s. So there's only about a 10-degree temperature difference in terms of average temperatures per 1,000 miles as we go from Iowa to the Gulf Coast. Whereas in the wintertime, there was a 25-degree change over 1,000 miles from the Gulf Coast to Iowa. So the isotherms aren't as packed over the land masses. Also notice that we begin, if we look over the ocean, that the isotherms begin to bend down here. They begin to bend up here. We'll talk about why that occurs here in a little bit. Again, if we look at the southern hemisphere, pretty much straight across. Not a whole lot of change in terms of the packing of isotherms. Do you notice this area right here? Notice it has a bullseye of 70-degree temperatures. What do you think the reason for that is? Well, that has to do with elevation. That's an effect of temperature. This is where the Himalayan mountains are located at. And so we're seeing the effects of elevation there. Also notice this area of 90 to 100 degree temperatures. Also notice 90-degree temperature here. Now notice that this is in an area near 30 degrees north latitude. Do you recall we talked about that being an area of very little cloud cover, very little vegetation, very little moisture? And so what we see along this particular area is most of the energy coming in from the sun being used for sensible heating. Now if we go back to the average January temperatures and we look at the southern hemisphere, notice we have 90-degree temperatures here. Over here, over this continent here, that's Australia. And notice where that's located, at about 30 degrees south latitude. So some observations are to summarize in terms of the controls of temperatures. Temperatures typically decrease as you head poleward. We have a tighter packing of isotherms in January compared to July. And we'll learn why that occurs here in a few lectures later. Notice also the bending of isotherms near ocean-land interfaces. That has something to do with the heat capacity of land compared to oceans. And then I chose a line of latitude and I compared continental temperatures versus oceanic temperatures at the same latitude. Some of the things that we notice, the isotherms bending up or down on both coasts during the summer months, and we ask why. And we'll talk about that in just a little while. What I'd like you to do at this point, we have some information on air temperature data that I'm not going to cover at this point. I'm going to ask you to read pages 72 through 74 for terminology. Some of the terminology is how they come up with average temperatures. One term that I will define from this particular set is what we call the daily diurnal range of temperature. Diurnal being the key word here. This is defined as the difference between the maximum temperature and minimum. In other words, the range. The daily high, the daily minimum, we call that the diurnal, which means as we go from day to night, change of temperatures. We'll look at some of the characteristics of diurnal temperature and some actual practical applications of using the temperature data. First of all, before we actually look at some of the practical applications, let's talk about characteristics of diurnal range of temperatures. Typically, the largest diurnal range is at the Earth's surface, typically larger on clear days. Largest range, or the largest range of temperatures, occurs on high deserts. Typically, the diurnal range is smaller in humid regions. Part of that has to do with the fact that the incoming energy is being partitioned off into sensible and latent heat of evaporation, and so not all of it's being used for sensible heating. Typically, the diurnal range is smaller at coastal cities. In other words, if you were to look at the average temperature let's say in Mobile, Alabama, along the Gulf Coast, the difference in the maximum temperature and the minimum temperature in the summer is not going to be very much compared to here in Iowa. For instance, Mobile may hit a high of about 85 and a low of about 75, so there's only a 10-degree difference. In other words, that range difference in temperature is about 10 degrees. You look at Iowa, we might see a high of 90 and a low of about 65 or 70. And so we're talking about a 20 to 25 degree difference at the same time. And so obviously the humid regions, the change in temperature is not as great. Smaller coastal cities, smaller in the concrete jungle. You look at urban heat islands, that's a term, basically where you have a lot of concrete. If you look at Des Moines, Iowa, one of the things I would ask you to pay attention to when you're watching the nightly weather forecast is look to see what the minimum temperature is in Des Moines compared to, let's say, Ames. Typically, Ames is going to be a few degrees cooler. Or if you look into southern Iowa, they may be a few degrees cooler where you don't have so much concrete. You should be prepared to discuss all the physical mechanisms responsible for the above diurnal range characteristics. And we've talked about these, and I've mentioned a few of these here. Let's take a look at some of the practical applications of temperature data. We'll look at these in terms of what we call heating degree days, cooling degree days, and growing degree days. Heating degree days, this is based on the assumption that people will start using their furnaces once the mean daily temperature drops below 65 degrees Fahrenheit. Recall that the mean daily temperature is defined as the max and min temperatures averaged together. And so the formula for this is the 65 degrees Fahrenheit minus the mean daily temperature. So for instance, let's say that the mean daily temperature for today was 55. We would take the formula 65 minus the 55 degrees Fahrenheit, and we would accumulate 10 heating degree day units. However, if the mean daily temperature is greater than 65, then there are no heating degree days. What you're looking at here is an average of heating degree days during the winter time. You'll notice along the Gulf Coast, not a whole lot of heating degree days. As we progress further north where it gets colder, as you would expect, the heating degree days would increase. And so as you go from south to north, heating degree days begin to increase. Next item we'll look at are cooling degree days, and this is just based on the assumption that people will begin to use their air conditioners when the mean daily temperature rises above 65 degrees Fahrenheit. So this is for the warm months of the year. The formula is the mean daily temperature minus 65 degrees Fahrenheit. So for instance, let's say that we have a high temperature of 90 and a low temperature of 70. Our mean daily temperature would be 80 degrees minus 65, and that would give us 15 cooling degree days. Again, if the mean temperature is below 65, then there are no cooling degree days. So basically, the use of heating degree days or cooling degree days are made decision-making processes for such industries as power, gas companies, construction companies. For instance, power companies during the summer will expect an increase in energy usage once we get above 65 degrees, whereas during the wintertime, oil companies, gas companies will expect more use of furnace as we go through the wintertime. What you're looking at here are cooling degree days. Again, we're talking about during the summer, and as you would guess, cooling degree days are higher in the south than they are up in our neck of the woods. Now, growing degree days is something that probably many of you are familiar with. This is an index typically used by farmers as a guide for planting and harvesting. There are multiple ways of calculating growing degree days, but the most common one, especially used here in Iowa, are what we call using the mean daily temperature. We use this because the main factor in terms of physiological development of plants is temperature and moisture to a certain degree, but temperature is a good indicator. The formula for heating degree days is the mean daily temperature minus 50 degrees Fahrenheit for corn. Now, depending upon the type of crop that you're planting and harvesting will determine what your base temperature is. And there is a table here, table 3.2 in your textbook, that lists the base temperatures for crops such as beans, corn, cotton, peas, rice, and wheat. Notice those of you from Indiana, any of you have any relatives in Indiana, the base temperature for wheat is 40 degrees. Sweet corn itself can be harvested when you accumulate 2200 degree days, growing degree days. One caveat, though, with this is if the mean daily temperature is above 86 Fahrenheit, the crop will become stressed and thus inhibiting the maturation process of the corn. So let's just take a typical July day. Our average temperature might be 80. And if we're looking at corn, we subtract 50, and that's 30 growing degree days for that particular day. And so this is a good practical use here in the Midwest for growing degree days. What I'd like you to do is to close out the material from pages 77 through 81. I'd like you to read through that. You will be responsible for identifying the different types of thermometers that are used in there and briefly describe how they function. Nothing in detail, but just a brief description of how they function are the things that you'll be held responsible for. Well, this is the end of Chapter 3. I hope you've learned quite a bit, and have a good day.